Okay, so far we've just been dealing with discrete probability distributions, okay? And now I want to focus on some probability distributions that can have a continuous range, okay? So we're going to consider continuous probability distributions. So to say here, we consider distributions that have a continuous range of values. So for example, they could be over an interval of values, they could be over all the positive numbers, all the positive real numbers that is, or it could be over all of the real numbers, okay? So the thing to say is that these continuous probability distributions are defined by a probability density function. So remember before, when we were considering discrete probabilities, we were looking at a probability mass function. We sort of imagined each probability putting some sort of weight on different numbers, okay? Now that we've got a continuous range of numbers, we can sort of imagine us putting a surface over the range of numbers and considering the density of that surface at each point, okay? So not placing weights, but we're placing over some material that has different densities and thus different weights at different points, okay? So it sort of works sort of fairly, it's a fairly good analogue between the idea of mass, as in putting a weight in a certain place, or density, something that has varying weights over different places, okay? But anyway, that's just an analogue. Let's give the proper definition. So definition of a probability density function . Okay, a probability density function or is it sometimes called PDF? Okay, so not like a PDF file, but a PDF here meaning probability density function, is a function f that goes from, say, the real numbers, or whatever the range of your random variable is, to the positive real numbers, okay, so it could be 0 or greater, all right, that has the two properties we've kind of specified one of them already, and that's that f of x is greater than 0 for all x belonging to the real numbers, okay, and it integrates to 1, okay, so the integral over all of the real numbers, okay, in the domain of the function is equal to 1, all right, and that's it. So then, from this, we can define a probability distribution, okay? And the random variable associated with that distribution. So continuous probability distribution. Okay, so a random variable, let's call it x, okay, with values in the reals, okay, has a continuous probability distribution with probability density function, I'll just write PDF because it's a bit long to write, with probability density function f of x if I can find the probability that x is less than or equal to little x by integrating up to x my probability density function. Alright? And that's it. So once I've got this probability mass function, I just integrate it, okay, over the appropriate range of values that I want in order to calculate the probability of that event occurring. Okay. One point to add to this is the function and I'll just add a little bit of notation. Let's just call this f of x. The function f of x here is called the cumulative distribution function. I'll tell you what, I'll write that on a new line. Cumulative distribution function, or CDF. And one thing to say is that the cumulative distribution function here doesn't have to be just for continuous probability distributions. I could define f of x equal to the probability that x is less than or equal to x for a discrete random variable as well. Okay, so I can talk about the cumulative distribution function for both continuous random variables, continuous probability distributions, and discrete probability distributions. Okay, when I specialize into continuous probability distributions, I start talking about a probability density function, and when I specialize into discrete probability distributions, we talk about a probability mass function. Okay, so some things I can say about f. Okay, so one thing I can say is that, well, it's a number between 0 and 1. So I just say that it satisfies the following properties: that it's between 0 and 1 because it's a probability. Okay. It is non-decreasing. Okay, so it goes up. It might go flat, but it always goes up overall. Okay. And if we're in the world of a continuous random variable, then the derivative of f of x is equal to little f of x. Okay? And that's for continuous distributions. Okay? The fact that it's increasing makes sense because, well, we're just including more things that can happen as I let x get bigger, so the probability should get larger. This one's a little bit more subtle. Notice that really what we're doing here is we're differentiating this integral, so the derivative of the integral is just the term that we're integrating inside by the fundamental theorem of calculus. So that's by the fundamental theorem of calculus. Right. So some things that we can say from once we know the CDF, the cumulative distribution function, we can do various calculations. Okay. So notice for instance, that if I want to calculate the probability that my random variable x is in some interval between a and b, okay, so I'm saying I've got b and a here, and I want to calculate the probability that my random variable lies somewhere in this interval. So open it this side and close it this. Well, I can notice that this is exactly the same as the probability that x is less than or equal to b minus the probability that x is less than or equal to a. That's because this event plus this event are disjoint, okay, and the union of those two events is this, right? Okay, so then this is just equal to f of b minus f of a, which in turn I could write as the integral between a and b little f of x dx. Okay, so essentially if I want to know the probability of landing in some range a to b, then I just integrate my probability density function in that range, or I just look at my probability mass function and deduct the two. Okay. A further thing to add is that for a continuous probability distribution, the probability that x equals x is going to be equal to 0, because the integral from x to x f of y dy, well, we're integrating over an interval that's got 0 length, and so the answer we're going to get is 0, right? So notice what this sort of means is there's actually 0 probability of hitting this boundary here, all right? So in other words, it must be that the probability of being less than equal to x less than equal to b, which is just equal to the probability that x equals a plus the probability that a is less than x and less than or equal to b. Notice this guy here, all right, this is equal to 0, all right, and so what we're just left with is this, which again is just going to give me the integral between a and b f of x dx. Okay, so in other words, I don't really mind about corners and edges here. All right, so the probability that a continuous random variable hits any given number is 0, but we can have a non-zero probability that it lands in some given range. Okay, right. Maybe another thing I'll add is we can consider the density function associated with more than one random variable as well. So maybe just write that out quickly. We can consider the probability density function of two random variables together. So if x and y are continuous random variables defined on the same probability space, okay, then we take their probability density function to be a function of x and y. Okay, so here, f is a function, all right, that goes from, let's say, the real numbers times the real numbers to the positive real numbers. So it has to be such that f of x, y is greater than or equal to 0 for all x and y, both belonging to the reals, and the integral, as you might expect, from minus infinity to infinity, from minus infinity to infinity, of f of x of y dx and dy is equal to 1. Right? So we can define a probability density function for two random variables together, and then we can calculate probabilities with that as follows. So from this, the probability that x is less than x and y is less than y is calculated by integrating, as you might expect. So we integrate over up to some value y, and then integrate over x up to some value x of x dash y dash dx dash dy dash. Okay. So we can extend our notion of probability density functions to more than one random variable quite easily. We just have a function of all the random variables that we're interested in, and then we can also talk about, for example, independence of those random variables. So we can see that if two random variables x and y are independent, okay, then, all right, then we can check that the probability density function of x and y is actually the product of the density function of each y and by x and y individually. Okay, so we just multiply the two together to get the probability density function of x and y. Okay, and that sort of makes sense given the definition above. Look, that the probability that x is less than or equal to x and y is less than or equal to y, well, that being equal to the integral of f of x, y. So I could just write this out as so notice here that this guy is really just f of x, y as above. Okay, well then you can check for yourself, all right, that I can separate out this integral. So I can notice this integral in x here has a constant f of y dash, which isn't affected by changes in the value of x dash. Okay, which is another way of saying what happens in x dash doesn't affect what happens with y. Okay, so I can take that out and put that at the front. Okay, and of course this here is equal to the probability that x is less than x. Alright, so then what I'm left with, and I could take that, once I've evaluated that, I can take that out the front because it doesn't affect the value of y. So we've got probability x dash is less than x times the integral from minus infinity to y, f of y dash dy dash, okay, which then in turn is equal to the probability x is less than or equal to x times the probability that y is less than or equal to y, right? Okay. Note further, if I had this same property, I could differentiate with respect to x and then with respect to y, and you'd see, so let's just do that. So we can see that if I have my probability density function of this form, then it must be that these events are independent of one another. Further, if we have that this holds, then, well, if I could arrive at my probability density function by differentiating this. Okay, that's exactly how we got our probability density function up here. I take my cumulative density function, right, and I differentiate it and I get my probability density function. The same is going to be true here. So you can imagine that f of x of y is equal to the derivative with respect to x and with respect to y of this. But if I differentiate this with respect to x and respect to y, we're just going to get the derivative of this guy with respect to x times the derivative of this guy with respect to y, which is just going to give me f of x times f of y. Okay, so that's why we end up with this kind of product structure for the density functions, just as we did for the probabilities themselves, like for the discrete case. Okay, and you can imagine that we can go working with these definitions, okay, to have 3 or 4 or 5 or any number of random variables that we like. Okay. All right. Okay. So that gives a basic introduction to the idea that continuous probability distributions just correspond to integrating a probability density function. All right. So the next thing you might want to consider is the expectation and variance of a continuous distribution. Okay. So let's have a think about that. So expectation and variance. Okay, so essentially, I'll even write this down. The expectation and variance for a continuous random variable behaves in the same way as a discrete random variable. We just replace summation with integration. Alright, so remember that integrals are just really sums, appropriate sums, okay? We can think of an integral as the limit of a summation, and you'll cover that in a calculus course, or at least you should cover that in the calculus course in Manchester. So really the kind of jump from dealing with expectations in discrete to expectations in continuous is really just a jump from sums to integrals. Okay, so let's give a definition to be a little bit more formal. Okay, the expectation of a continuous random variable x is given by the expected value of x, which in this case we're defining to be the integral from minus infinity to infinity x times the density of the probability density at that point x. Okay, so notice this is really just the sort of analog. This is just the same as doing a sum, say from n equals minus infinity, x equals minus infinity to infinity x times the probability that x equals x. Right? We're really doing the same thing, we're just replacing this with the density here and with an integral here. Okay? So it's really just the same thing. Alright? Similarly, we can define, the expectation of a function, of a random variable, or two random variables. Okay? It was just the integral of that function, of x applied to it, times f of x dx. Okay? And we can define the variance of x is equal to the expected value of x minus e to the x squared. Alright? Which is, again, by the same sort of calculations as before, is equal to e to the x squared minus e to the x all squared, which in our case is going to lead us to this integral minus infinity to infinity x squared times the probability density function at that point, minus the integral minus infinity to infinity x f of x dx, and then all squared like here. Alright? So really, the kind of calculations is not such a big step in terms of evaluating expectations and variances when we go from discrete to continuous. It's just the same as the step as going from summing to integrating. Okay. One thing I should add, I'll just scroll up to grab it, is that really all of the same properties that we were dealing with discrete random variables are going to pass over to continuous random variables. Okay, so specifically, let me just go up here. So the sorts of rules that we're considering in this lemma, right, you might as well verify for yourself that this lemma is going to hold also for continuous random variables. And if you look at the kind of proof that we're just doing for each case, notice really we're just going to replace each of these terms with an integral, okay? We're just applying the appropriate properties of the integral in each case, right? So the proofs are essentially going to run in exactly the same way as previously, just replacing some of these sums with integrals and applying the appropriate substitution rules. Okay, so I'm not going to go over that now, but rest assured, essentially, because the same sorts of properties that summations hold apply to integrals, we can then apply exactly the same lemma as previously for discrete random variables. Okay? Right. Okay, good. Right, that's what I wanted to say so far about continuous random variables. Next I'll start to look at some specific distributions, or one specific distribution that's a continuous distribution called the normal distribution. It's one of the sort of most important probability distributions that you'll come across, and that's why one of the reasons we kind of make efforts to cover continuous distributions at this point is so that we can show you what a normal distribution looks like. Okay, great.